Hello everybody, Mr. Hennon here, and today we are going to start looking at chapter 15 on thermodynamics. I'm just going to look at a couple of the laws today. This one's kind of weird because there are actually 4 laws of thermodynamics, but they only go to the 3rd law of thermodynamics because they developed the 1st, 2nd, and 3rd, but then as they had already developed some, they realized that they needed another one that would actually precede the 1st law, but rather than renumber them, they just call it the Zeroth Law. So thermodynamics is really this branch of physics that's built upon the fundamental laws that heat and work obey. It's because when we have some kind of system, and this system is usually going to be like a gas, and that for us, we're going to normally look at it as a gas. We talk about the work being done by the system or work done on the system, heat going into the system or heat coming out of the system. These are all going to be important. So we're going to be talking about the system and the surroundings, so which direction things are going, and we can have heat flow in and out if we have what we call diathermal walls. And then later on we'll talk about the word adiabatic, but adiabatic means it doesn't allow heat to flow. So all those are going to kind of pop up. So when we start out and we talk about the Zeroth Law of thermodynamics, we really are talking about thermal equilibrium, and it really allows us to measure the temperature of something, that we can actually measure temperature. Because the idea is, let's say that I have some container A with a gas, and I use a thermometer and I measure the temperature of it, and it's a certain value up here. And then I take that same thermometer and put it into object B here, and I measure its temperature, and I happen to notice that they're at the same temperature. What can I say about A and B? Well, if I were to connect them with diathermal walls, in other words, I would allow heat to flow back and forth between them, since they're at the same temperature, we know there shouldn't be any heat flow happening between these two because they're in thermal equilibrium. So really the Zeroth Law popped in so that we could say if 2 systems were in thermal equilibrium with a third, that they also must be in thermal equilibrium with each other. So it basically says you can use a thermometer to measure the temperature of something, and once those are in thermal equilibrium and we know that something else is at that same temperature, then we can also say it would be at thermal equilibrium. That's really all the Zeroth Law does. It allows us to measure temperature. There's really nothing extra special about it. The next one that really gets into the system is the 1st law of thermodynamics, probably one of the most important. And really, if it boils down to, the 1st law of thermodynamics is really just the law of conservation of energy. But what we're going to break it up into is internal energy and heat. And also we'll eventually be talking about the work. So internal energy is going to be measured with a lowercase or a capital U here. So this is the energy of the system. And basically one part of it is if you have a change in internal energy, it's because you have some of that heat going out or some of the energy going out as heat or coming in as heat. And so one of the key ideas is heat is going to be positive when the system is gaining heat, and it's going to be negative when the system loses heat. So our change in internal energy is equal to the heat is one concept or one part of our conservation of energy. The other thing that we can have is work. Work can be done on the surroundings or work can be done by the surroundings. So here we're going to assume that there is no heat flow. Again, conservation of energy indicates that the internal energy of a system will decrease if work is being done on the surroundings or on the environment. So we write that as delta U equal to negative W because we're actually decreasing the energy, so we're actually working on our environment. And so work is positive when it's done by the system and negative when it's done on the system. So we want to keep that in mind. So it's done by the system or negative when it's done on the system. Those are key words. The 1st law of thermodynamics pretty much boils down into this equation right here. The change in internal energy is equal to the final energy minus the initial, so that's just our normal, but it's equal to Q minus W. So it'd be the heat plus the work. But since changing internal energy is being done on the surroundings, that's decreasing that when it does on their surroundings and increasing when it's done on the system, that's what's going to affect it. Probably the most important part of this equation is this little statement down here that heat is positive or work is positive at certain points. So we want to make sure we have all of this. So let's try a little example. Let's say that I have some system. Maybe it's just a gas here. And in this gas, in this first situation, the system is doing work on its surroundings. So maybe it's a gas that pushes against the piston. So it pushes against its surroundings, but you're adding heat to the system. So heat is going into the system. So I love this little picture over here to kind of help. So in figure A, they give us some numbers here that the system gains 1,500 joules and 2,200 joules of work is done by the system. So in this particular case, determine the change in internal energy of the system. So in part A, to figure out that change in internal energy, we know it's equal to Q minus W. But it's important what kind of W's and Q's we put in. So if we are gaining heat, we put that in as positive. So that would be 1,500. So put in my 1,500 here. But then it's being done being done by the system. So it's doing work on the environment or on the surroundings. So that's going to be a positive work. So we have minus the 2,200. And so when I figure that out, the change in internal energy of this system, since it gained 1,500, but it lost 2,200, it's basically going to be a negative 700 here. So negative 700, and it's just joules. Ta-da! So that's the basic idea of the first law of thermodynamics. The second part looks very similar. It's got the same numbers, but the key thing here is work is done on the system. In other words, imagine that this gas is in a container and you push against the piston that compresses that gas, and you also are adding heat to it. If I do both of those at the same time, that's going to make that internal energy skyrocket. So in this particular case, in part B, the change in internal energy, which is still Q minus W, we have the 1,500, but when we try to figure out that 1,500, what exactly it's doing, that's still positive because it's added to the system. But when I add or when I subtract my work, since it's being done on the system, this is negative work. So it'd be a minus a negative 2,200 joules. So it's actually like I'm adding the two values together. This is going to cause an increase in my internal energy, and this would be 3,700 joules, sorry. Can't add 3,700 joules. So this is one of the key things, is that on or by is going to be very important as we're trying to figure this out. So I'm going to stop there for the first law and the zeroth law. We'll work some more with them as we get into more thermodynamics in chapter 15. I hope you enjoyed this beginning Henstitute video. Take care.